Okay, in this screencast, we're going to have an introduction to direct current electrical circuits, and we're going to learn how to do a little analysis of the circuit. And DC, by the way, just means direct current. So that word DC is direct current, and that means there is a power supply, probably a battery, connected to the circuit that allows the current to go in one direction. This is different than in your house, which has AC current, which alternating current. It goes back and forth in different directions 60 times a second, believe it or not, because of the way electricity is generated at the electrical company. But direct current, which is all you need to worry about for AP Physics 1, and it's current that's supplied by a battery. We learned in the last screencast how like charges repel each other, unlike charges attract. Well, a battery is a source of electric potential energy. It uses chemical potential energy to create, to pile up charge on one side, positive charge. So for instance, we'll have the long line here represents the positive terminal of the battery, so this is like the positive terminal. The shorter line is like the negative terminal. So I've got a bunch of negative charge piled up over here on the shorter line side. So that symbol represents a battery in a circuit. Sometimes you'll see it represented with more than one line like that. That just means it's still a battery, it just might be a little higher voltage. A resistor is represented by these squiggly lines. A resistor is anything that uses the power created by the battery. So in your house, it's any of the electronics that you use in your house. Lights act as resistors. TV, I guess that would be an electronic. Space heaters, toasters, things like that. Okay, so any of the appliances act as resistors. So resistors use the electricity provided by the battery. The black lines are just the wires in the circuit. Let's talk a little bit about the theory behind what makes the current flow through the circuit. And it's easy to think of this in terms of water with a pipe. So when you think of a battery, you can almost think of like a pump that is pumping water from one tank into another tank. Here's a pump with these two beakers here, pumping water from beaker B into beaker A. So it takes the water from one side, pumps it into beaker A. Because there's another connection here between beaker A and beaker B, the water can just flow back into beaker B when it gets higher over on this side. Water doesn't want to be higher on one side than the other, so it naturally is going to flow back through that bottom connection there, through that bottom pipe. The battery is kind of like that pump, but instead of water, it's piling up charge. So it's got charge separated. It's got a bunch of negative charge at one terminal, and you know that negative like charges don't like to be next to each other. So there's a force exerted on them that's going to push them through that conductive wire. What makes a wire conductive, like copper, silver is a really good conductor, but silver is a lot more expensive than copper. Copper is nice for wires because it's malleable. You can form it, shape it, to go around corners and things like that. And because it's a conductor, it's metal, it has, has a lot of free electrons. Electrons are the things that actually move through the wires. Protons are stuck in the nucleus. A conductor is a conductor because it's got free electrons, and those electrons flow through the battery, the wires, and the bulb. Okay, so they come back through here, attracted to the positive terminal, and the battery pushes them out again. Sorry about that. So that kind of gives you a summary of how you can compare an electrical circuit with water in a pipe. Now we need to talk about what really happens in a battery versus the convention. As I mentioned, with a battery, the direction of movement of the electric charge in the battery is that electrons move from the negative terminal to the positive terminal. Electrons are the things that are free in the atom to be released and to move through the wire. Unfortunately, not unfortunately, it's just the way it is. Ben Franklin, who actually did a lot of work in electricity, believe it or not, defined the positive and the negative charge. He was the first guy to discover that there's two different kinds of charge. He called one positive, one negative, and he made the random assumption that the positive charge is the one that moves. And so for the next several decades, all the work in electricity assumed that positive charges moved. And so a convention was established that positive charge carries the current through the wires. Unfortunately, that's not true, and after that was discovered, the convention had already been established for many decades, and so it just stayed that way. And so that's just the way that I will show you as I analyze these circuits. And from now on, just know that we always define current as a direction that a positive charge would move. For the AP test, you might conceptually need to know that in reality it's the negative charge that carries the electricity in the opposite direction. Okay, well, let's talk a little bit more about the different arrangements of resistors in a circuit. And the first one I'm going to show you is resistors in series. When resistors are in series, we show our battery here, positive and the negative terminals, the current is going to flow this way. And what it means to say resistors are in series, it means that all the current that flows through one resistor is going to flow through the next one and the next one. So there's no alternative path for the current to go. It's always going to go, all the current's always going to go through each resistor. So we say that they are in series. In other words, one right after the other. So I'll just write it down here. Resistors are in series when there is no other path for the current to flow. There's only one way for the current to go through that circuit. It's going to go clockwise, again, as if it was a positive charge carrying the current, and it would go in that direction. Okay, now that is not true for the next arrangement, which is resistors in parallel. Again, I've got my battery here, positive side, negative side. So the current is going to come out in this direction. I'm going to call this I1. I1 gets to this point right here, this junction, and it's going to split. It's just like, water flowing through a pipe, and it gets to a T in the pipe. It's got two alternative directions that it can go. So we will say this is going to be I2, and this is going to be I3. So you can see there's conservation of charge that we learned about in the last screencast. So all those electrons that make up current I1 are going to be split into current I2 and I3. So hopefully you can see that I1 is made up of all of the electrons in I2 and I3 combined. So it's just splitting into those two. When those electrons get back to this point right here, so all the I3 current is going to flow through that resistor, and then it's going to come down here and flow through that bottom of that branch. I2, meanwhile, comes back, and they meet again at this bottom junction right here in blue that I just highlighted, and they're going to meet again and combine to form I1 again. So that same amount of current as came out of the battery is going to come back into the negative terminal of the battery. So resistors are in parallel. Are said to be in parallel when there is an alternate path for the current to flow. And the word parallel, you can kind of look at the diagram and see those two branches are drawn, so that they're parallel vertically. So I think that's where that name comes from. But it just makes it easier to look at when they're drawn parallel to that. It doesn't mean they're actually configured that way in the wires in your house. Okay, let's talk about how we analyze a circuit. We're going to use something called Ohm's law. Okay, again, here's my battery, positive side, negative side. Wow, I got orange somehow. Positive side and negative side. I'm going to give these some actual values. So I'm going to call my battery, it's going to be a 9-volt battery. So the voltage is 9 volts. I'm going to say this is a 2 ohm resistor. I'm going to call this a 3 ohm resistor. And I'm going to call this a 4 ohm resistor. Current is going to flow this way from the positive terminal to the negative terminal. And it's going to go clockwise. Well, I'd really like to know how much current is in the wires, because that's how electricians know how to size the wire, based on how much current is in the wire. If there's going to be more flow through the wire, just like a pipe, you'd want a bigger pipe. Same thing with wires, you want a larger wire. Wires heat up when current goes through them, so if you have too much current going through a small wire, it could overheat, it could cause a fire. So when you do circuit analysis, you're trying to figure out how much current is going through each branch of the wire. And circuit breakers are also sized for that reason. A circuit breaker in your house is designed to trip or break the circuit when there's too much current flowing through a wire. So you put too much stuff onto one circuit in your house. Maybe a space heater, a vacuum cleaner, a refrigerator, all on the same circuit, and it's going to blow the circuit breaker because you got too much current going through that wire, and it's going to overheat and maybe cause a fire. So because these are in series, all the current flows through, the same current flows through all 3 resistors, that value I there. We don't know what it is, but we're about to figure it out. Ohm's law says that voltage is equal to current times resistance. So what that means is if the resistance is constant, so I'm going to assume that all these resistors, the 2, the 3, and the 4 ohm resistors are constant. As I increase the voltage through the circuit, then I is going to increase. So that graph would look like this. Voltage versus current, it would be a linear graph, and the slope of this would be R. This is not a law of nature. Individual devices, in other words, like your toaster, things in your house, if they follow Ohm's law, in other words, as you increase the voltage, if the current goes up through that device, it's called an ohmic device. Not everything is ohmic. In other words, for an example, a light bulb. If you turn on a light bulb, that filament heats up in a traditional incandescent light bulb. And as the filament heats up, the resistance increases through that filament. And as the resistance increases, less current goes through it. So that graph ends up looking like this. So you can increase the voltage, but you're not going to get much more current through it as you move to the right on the x-axis. So notice that that would be like a light bulb, and that would be non-ohmic. You might need to know that conceptually for the AP exam. There's 2 different kinds of materials. Everything that we work with, all the resistors that we work with, we'll call them ohmic, which means the resistance is constant. So let's analyze this circuit and figure out what the I is using this equation, Ohm's law, that we just used, V equals IR. That's like the F equals MA of the electrical circuit world. So we'll be using that throughout the analysis, V equals IR. Okay, well, we know that actually across each one of these resistors, there's a little bit of loss of energy, a loss of voltage. So there's a little bit of delta V across the 2 ohm resistor. I'll call that delta V1. There's a little bit of loss of voltage across this one, and there's a little bit of loss of voltage across this one. Well, the loss of voltage across all 3 is going to be equal to the 9 volts that we put into the system. So the delta V total, that's the total change, is the sum of those 3, and that's going to be equal to the 9 volts. Is equal to that, which you have up there. Okay. So I know that the change in the voltage across 1 using Ohm's law is equal to the current that passes through there times resistor 1. Using Ohm's law again, for resistor 2, that change in voltage across resistor 2, the loss of energy, is equal to the current that passes through that second resistor times the magnitude of that second resistor. And then likewise for V3. So I can substitute all these in, these guys here, I can substitute in to this equation right here, and we can solve for I. So my 9 volts is equal to I times R1 plus I times R2 plus I times R3. And notice that it's the same current through all three of those, so I can factor out the I and just have R1 plus R2 plus R3. Now, what we're doing when we do that is we're finding something called the equivalent resistance. So in a series circuit, the resistance of the circuit as a whole is equal to the sum of the individual resistors. I'm going to call this REQ. And when I put the actual numbers in there, that's just 2 plus 3 plus 4. So the 9 volts on the left side equals, I times 9. Divide both sides by 9, and I get the current in my circuit is 1 amp. And I got that just by dividing both sides by 9. I've got my 9 volts on this side, so divide that by 9, and I get 1 amp on this side, or 1 amp for my value of I. So that allows me to size my wire, that allows me to pick a circuit breaker. I know exactly how much current is going to flow through that circuit if I hook up a 9-volt battery. This idea of equivalent resistance, what that means, it's as if instead of 3 separate resistors, it's as if I hooked my 9-volt battery up to a single resistor that has a resistance of 9 ohms. So when you find the equivalent resistance of a circuit, what you're doing is you're combining all the resistors, all the things that are attached to that circuit, and boiling them down to one individual resistor, and it makes the circuit analysis very easy. And we use that to figure out how much current is flowing through each branch. Okay, so now let's analyze a circuit where the resistors are in parallel. And this will be a little bit different. We've got our battery here. I'm going to keep it as, let's make it a 12-volt battery. All right, so it's going to be a 12-volt battery, and let's say I've got a 4-ohm resistor here, and let's say I've got 3-ohm resistor here. So I've got my current that's going to come out of the battery in this direction, from the positive direction to the negative direction, I1. It gets to this junction right here. It's going to split. I'll call this I2 right here, and I'll call the current in this direction I3. Those are going to come through here and here, and they're going to meet again at this point right here, and I will have I1 back again when they merge. So the big idea in this one was, or the equation is I1 equals I2 plus I3. Now something to think about in this case is the battery has electric potential energy stored in it. It's taken the chemical energy of the chemicals in the battery, and it's used that chemical energy through reactions to separate positive ions and the negative charge. Okay, so you can almost think of this battery, electric potential energy stored in the battery, as if it was, when you think of gravitational potential energy, you can kind of compare it to that. When you take a boulder up to the top of a cliff, it's got all this gravitational potential energy, and you might define your 0 point for your gravitational potential energy down at the bottom of the cliff. Well, I'm going to define my 0 point for my electrical potential energy to be at this point right here. This will be the negative terminal. I'm going to say is at 0 volts. That'll be my reference, just like my gravitational potential energy. And the top terminal will be 12 volts. Well, you'll notice along this branch here, I'm tracing it in blue. When I get up to this node, there's no resistors anywhere to diminish the amount of voltage in that wire. I'm going to assume the wire is perfect, kind of like a frictionless surface. That's a good analogy for that. So that would mean I have 12 volts at that point right there. Following along here, I have 12 volts at this point too. Down here on the 0 volt side, if I think of this bottom terminal on the battery, that's at 0 volts. I trace this back to this junction here. I have 0 volts there. I have 0 volts there. Following the same logic, there's no resistors to diminish or change that amount of voltage. Why is that important? Because when I do this analysis, when I apply Ohm's law in this case, I'm going to apply it to try and solve for the amount of current in each branch. So I2 is going to be equal to the change in voltage across resistor 2 divided by resistor 2's value. So I've just rearranged Ohm's law. I've divided both sides by R, moved the R over to the other side there, and likewise I3 is going to be equal to the voltage drop across resistor 3 divided by R3. So substituting those into the formula up above for those I2 and I3, I get I1 is equal to the change in voltage across 2 divided by R2 plus the change in voltage across divided by R3. But I1 represents the total amount of current going through the circuit. See, remember I1 is this amount up here, this amount down here. It's the sum of those other two. So I1 is just the total voltage of the circuit, which is the 12 volts, divided by the equivalent resistance of the circuit. You know, the total, I should put a delta in front of that, divided by the equivalent resistance of the circuit. So what I'm going to do here is I'm going to get an equation for, a general equation for the equivalent resistance of a parallel circuit. So I1, I'll substitute that in for I1, delta V total divided by Req equals delta V2 over R2 plus delta V3 over R3. But notice the total amount of voltage, that 12 volts, is the exact same as the voltage across each branch. Remember, we had 12 volts up here, 0 volts down here, 12 volts up here, 0 volts down here. So these are all the same, left side and the right side. So I can divide by that 12 volts, and these would all cancel out. So that gives me an equation for the equivalent resistance of the circuit, that Req is equal to 1 over R2 plus 1 over R3. I guess I called them 2 and 3 because that was the branch. Okay, so the equivalent resistance for the whole circuit then is, if I go to the next slide, so the equivalent resistance is equal to 1 over R2 plus 1 over R3, which from that last slide, 1 over 4 ohms plus 1 over 3 ohms is equal to 0.25 plus 0.3 repeating is equal to, we'll just say 0.58, but that's equal to 1 over the equivalent resistance, right? So the most common mistake that people make in finding equivalent resistance for the parallel circuits is forgetting to do that last step of finding the inverse of the 1 over 0.58. Might have been easier if I kept this with fractions and combined those two, because that would be 3/12 plus 4/12 equals 7/12. So the inverse of that, the equivalent resistance, is 12/7. So in decimal form, let's see what that would be. I'll take it offline for a second. So the equivalent resistance for that circuit is about 1.7 ohms. Okay, so that's like saying I take this 4 ohm resistor and this 3 ohm resistor, and it's like having a single 1.7 ohm resistor in the circuit. Okay, So now we know what I1 is going to be, because I1 is the total amount of current that's coming out of that battery. Right there, that's my I1 right here. So I1, applying Ohm's law, is the voltage at 12 volts divided by the 1.7 ohms. That's going to be about 7.06 amps. All right, so that's how much current I have going through at I1. So that would be over here, this would be my 7.6 amps. It's going to break into I2 going that way and I3 going this way. So now to figure out I2 and I3, to finish my circuit analysis and figure out how much current I have going through those two individual branches, I can come down here and I can say, I2 is equal to V2 over R2, which is 12 volts over 4, and I can say I3 equals 12 volts over 3, and so you can see pretty quickly that this is 3 amps and this is 4 amps. The reason I'm off by a little bit here, 7.06, is I rounded my, this should have been, you know, if I wouldn't have rounded off, I'd have 1.71 ohms there. And if I divided by 1.71, this would have been exactly 7 amps. Because you'd expect I2 and I3 to add up to I1, which is not 7.6, it's 7.06. I see I made a mistake up here. It's 7.06. Had I not rounded off, I would have gotten exactly 7 amps there. So as you can see, that I1 adds up to I2 and I3. And notice that I2 is a smaller current. This is 3 amps going through this branch right here. This is 4 amps going through this branch right here. And it's got the one with the larger resistance. This has a larger resistor here, the 4 ohms. So there's less current going through that branch. This has a smaller resistor. It has more current going through at 4 amps. They come together at this junction point, and you again have about 7 amps going through at this point here. Okay. So that's how you figure out how much current is in a circuit with resistors in parallel. Finally, to summarize this idea of equivalent resistance, I would say for resistors in parallel, or in series, let's start with series, that's the first one I did. The equivalent resistance is as easy as adding up the values of the individual resistors and then getting an answer for the equivalent resistance. For resistors in parallel, you find the reciprocal of the equivalent resistance by adding up the reciprocal of the individual resistors in the circuit. And again, the most common mistake that's made is students will figure all these out on the right side here, all these different reciprocals, and add them up, and they'll forget that the answer they get when they do that is the reciprocal of the equivalent resistance, not the equivalent resistance itself. So after you add all these reciprocals up on the right hand side over here, don't forget on your calculator to do that last step and find the inverse of whatever the number is that you get there. Okay? All right, that's it for this screencast. I know it was a long one. The next one will be strictly, well, it will be analyzing a combined circuit with both parallel and series resistors in the same circuit, and I'll show you how to break that down and simplify it. Okay.